we've now learned about galaxies, and we've talked about stars and how they evolve and different types of stars. And for the most part, I've told you that stars, the light output from stars will be constant over their life cycles, at least while they're on the main sequence. But there are some interesting cases where that brightness will change, and we can actually use that to measure the distances to these faraway things in the universe. So we'll talk about variable stars today, and then what we call the cosmic distance ladder, which is how we measure different distances out in space and put them all together to measure distances to the very farthest things we can observe. So to start, we talked about galaxies last time, and there are different types. There's the spiral galaxies, which some of them have bars and some of them don't. And within the spiral type of galaxies, there's different amounts of spiral arms that you can have, and whether they're very prominent or not. And then there are elliptical galaxies, which just have the central bulge and no spiral arms. And then there's also the irregular galaxies, which are kind of in between the spiral and the elliptical. And we said that a lot of the elliptical and irregular galaxies are coming from the mergers of these spiral galaxies. So what did we say was at the center of all of these galaxies? Yeah, so it'll be a supermassive black hole. So stellar mass black holes are just kind of in random places in space where a big star died, but the supermassive ones are at the center of galaxies. Globular clusters are usually in the halos of galaxies, and then some galaxies have an active galactic nucleus, and we think all galaxies at one point went through an active phase. But, for example, the Milky Way galaxy doesn't have an active galactic nucleus, but it does have a supermassive black hole. Okay, so variable stars are basically stars that do not have a constant light output, even though they appear to be on the main sequence. So main sequence is when you're turning hydrogen into helium in your core, and so there has to be some interesting physics going on to disrupt that constant light output. And you can see a picture here, January from one year to December of another year, and the brightness of that star appears to have changed. So one type of variable star is a Cepheid. So Cepheids are typically higher mass stars, and they have a period that's on the order of tens of days. So this example, the period of this one is 50 days. And because these are higher mass stars, they're going to be younger stars. Put that in contrast with RR Lyrae. So these are stars that are typically lower mass stars, so they can be much older, and they have fluctuations over like less than or around a day. So this example, the period of this oscillation is about half of a day, and you can see the change in magnitude is about 1 from the dimmest the star will be to the brightest it will be. And the way that these stars have this brightness variation is called the kappa mechanism. So the chemical responsible for this is doubly ionized helium. So regular helium is going to have a neutral charge, and it has 2 electrons. So if we knock off both of those electrons, then we have doubly ionized helium. So ionizing is just getting rid of the electron. So you need a lot of energy or a lot of temperature to ionize the helium, and so this is happening deep within these stars, and it turns out that doubly ionized helium is more opaque than singly ionized helium. So opaque meaning it doesn't let light pass through it. So you can get a layer of this doubly ionized helium forming in a star, and then because the doubly ionized helium is opaque, any of the photons generated in the core that are trying to escape the star are just trapped within this layer of doubly ionized helium. So from the outside of the star, it appears that the star gets dimmer because those photons that would normally be escaping are instead being trapped. If you trap a bunch of photons, you're trapping a bunch of energy and heat, and so when something heats up, it expands, and so the star will expand, and as something expands, it cools down. So you needed a certain temperature to doubly ionize that helium. Once the star expands enough that its temperature drops, that doubly ionized helium will start to capture electrons and become singly ionized helium again. Singly ionized helium is not that opaque, and so the photons that were getting trapped are now able to pass through that layer and escape the star, and so the star brightens back up, and now because those photons are not getting trapped, that heat is not being trapped, so the star can contract. As the star contracts, it'll start to heat back up, and the process continues. So that's why we get the constant dimming and brightening, is because of this kappa mechanism. And it can continue for a very long time because none of this is terribly destructive. So it's not like some big explosion that's happening that's making it brighten and dim. So the periods of the Cepheids and the RR Lyrae are very consistent because of the physics of the kappa mechanism. And so if we put these variable stars on an HR diagram, they're in this kind of diagonal line called the instability strip. So they're kind of evolved off of the main sequence, and they're kind of perpendicular to the line of the main sequence on the HR diagram. Okay, so now I'll let you guys talk amongst yourselves for a minute or two. How could we detect these variable stars? So is it easy to see if something gets brighter or dimmer in the night sky? And if so, how could you do that in a very methodical way? Let's say you just take a bunch of pictures of the sky and see what you see. So in these two images, does it look like there's anything different between them? So where is there something different? Yeah, so astronomers are pretty lazy, so the interesting thing is going to be in the center of the image. But if you're having trouble seeing it, you can blink the two images and you can see either the new thing or the thing that's become a lot brighter pop up in the center. So as a human, we're kind of good at pattern recognition, so we can see when something changes in this grouping of stars. But we have too much astronomical data to do this manually. So instead, we use a technique called image subtraction. So if you just put one image on top of the other and subtract the pixel values, then anywhere there's an excess amount of light will be not subtracted away, basically. So using image subtraction, you can basically automate this process of trying to find new images or new sources in your astronomical images. And so we use that to find many new, what we call transient phenomenon in astronomy. Another technique that we can use is by systematically monitoring the brightness of stars. So this is a flaring star, and so you can see it increases its magnitude by about 2 over the span of just a few minutes. And so what you can do with this is, if you have this kind of baseline is what the star's normal activity is, you can train algorithms or machine learning algorithms to detect any variations in this kind of flat baseline behavior. And so this is research that I've done, and it's really how do you detect these transient or interesting phenomenon out in space using the data available to you. Okay, so now how are we going to use those weird variable stars to measure distances in space? And then once we can measure those distances, what can we say about the universe? So we've seen one method for measuring distance in astronomy, and that was the parallax method. So as the Earth is orbiting the sun, you get different viewing angles to these nearby stars. And so in January, we might see this yellow star kind of to the left of this grouping of stars. And then in July, we might see it more to the right of that grouping of stars. You can measure the angular distance of where that yellow star appears in the sky. And using that angle, you can do some trigonometry to calculate what distance that star must be away. So this technique only works basically within our own galaxy. And even then, it doesn't even make it all the way across the galaxy. So this is good for nearby stuff, but we're going to need even bigger or even better techniques for stuff that's farther away. And then within our own solar system, we can do things like using radar, which is just bouncing light off of something and seeing how long it takes to do the emitted trip and then the bounce back and receive that light again. So we've talked about brightness and luminosity. Brightness is how it's the flux, that's what we measure, and luminosity is the total energy that object is putting out. So if you had some object that always had the same luminosity, you could measure the brightness and then calculate a distance. So we call these things that have a set luminosity a standard candle. And so you can, just by measuring the luminosity, or just by measuring the brightness of this object, we can figure out its distance. So these are very useful for astronomy. And it turns out we can make the variable stars that we talked about act like standard candles. So what do I mean by that? So we have this RR Lyrae, it has this given period, and it turns out if we make a graph of the period versus the magnitude of the star, we get a nice linear graph. You have to do some logarithmic stuff, but that's not important for right now. So what this is telling you is that the longer the period, the brighter that star is going to be. So just by measuring the period of one of these RR Lyrae, which is just making this kind of graph and seeing where the peak to peak is, you can figure out what brightness it is and use that to establish a standard candle. And this works for distances up to 1 megaparsec. So remember, 1 parsec was the distance that something is away if it has 1 arcsecond of parallax. So this is a megaparsec, so it's 1,000,000 times farther than that. And we can do the same thing with Cepheids. So we can plot the period versus the luminosity, and we get a kind of linear graph, and that will let us just measure the period of the Cepheid, and then we can figure out measure the brightness, and since we know the luminosity, we can get the distance to that Cepheid. Another good standard candle is a type 1a supernova. So type 1a supernovae are the ones that were generated by a white dwarf in a binary system stealing mass from its partner, and if it exceeds 1.4 solar masses, then it blows itself apart. So that's the Chandrasekhar limit, and that's a relativistic limit for how much mass a white dwarf can have. So because this is a set mass, anytime you have one of these explosions, it had to have exploded at this mass. And so because it has, all of them should have the same mass when they explode, they should have the same luminosity. If you know what the luminosity is, you measure the brightness with your telescope, and then luminosity and brightness lets you calculate distance. So we can use these supernovae to figure out very long distances in space, and using these supernovae as standard candles was how astronomers discovered that not only was the universe expanding, but it was expanding at an accelerated rate. And we'll come back to that next week. So all of these standard candles come down to this equation. We can always measure the brightness just by pointing our telescopes out into space. If we can figure out some way to have a uniform luminosity, then we can get a distance out. So what makes something a good standard candle for astronomy? Yeah, so it's all about luminosity. So we don't know, we're trying to measure the distances, so we don't know if the object is going to be the same distance away or not. Some of the standard candles do pulsate, but like the type 1a supernova just has one big explosion and no pulsation. And then objects that all have the same size would be called standard rulers. So that's something that could be useful in astronomy. So if you know what size the object is supposed to have, and you measure its apparent angular size, then you could do some geometry to figure out a distance. But for candles, you just need the object to have a luminosity that you know. Okay, so we have a bunch of tools now that we can use to measure distances, but let's step back in time a little bit. So this is in the earlier part of the 1900s. We are looking through telescopes out into space, and we're seeing a lot of what at the time were called spiral nebulae. So remember, nebulae are just a collection of stars. So we were seeing what looked like collections of stars that were arranged in these spirals. And there was a lot of debate at the time about whether these were within our own galaxy or if these were separate galaxies way far out into space. And so Edwin Hubble is the astronomer who came up with the way of using the Cepheids as standard candles to measure distances to these galaxies. He did it first with the Andromeda galaxy, and the distance that he came up with was so big that this clearly had to be outside of our galaxy in a completely separate galaxy. So this is the person that the Hubble Space Telescope is named after. So not only did he show that these spiral nebulae were separate galaxies far away from us, but he measured the velocity of these galaxies. So if you take the spectrum of a galaxy, you might get something that looks like the top image. But when he measured the spectrum of these faraway galaxies, he was seeing that everything was slightly redshifted, meaning that everything was moving away from us. So this was the first evidence that the universe was not in a steady state. So another common belief at the time was that the universe was this eternal thing and everything was just static, and the universe didn't evolve or change. So this was some of the first evidence that that's not correct, and the universe actually evolves and changes over time. And so when he took these measurements for a bunch of galaxies, he found that the farther away you are in space, the faster you are receding away from the Earth. And we'll talk about next class, it's not that everything is moving away from the Earth, it's that everything is moving away from everything else. So it appears that everything is moving away from the Earth, but if we went to the Andromeda galaxy, it would also appear that everything is moving away from the Andromeda galaxy. So he made this graph, and the slope of this graph is called the Hubble constant, and the variable for that is h sub 0, and this tells you the velocity that something is moving away from an observer in space given its distance. So velocity in kilometers per second, and here the distance is in millions of light years. You'll also see different units for this constant as well. And so this is another way that you can measure something's distance. So if I know the velocity that something is moving away from me, so some distant galaxy, and if this is really a constant value, then if I take the velocity and divide it by this constant value, I'll get a distance out. So basically, look, using this graph, if I measure this velocity, I find where it intersects this line, and I can read off how far away that object must be. So this Hubble Law is another way that we can measure the distances to very far away things, just by measuring their velocity moving away from us. And so what the cosmic distance ladder is this kind of, each of these distance measurements are separate, but if you can stick them all together, you can get distances out to almost everything that you could imagine in space. So we can use radar within our own solar system. Within the Milky Way galaxy, we can use parallax. We'll talk about some other techniques in a minute, but you can use Cepheids to measure stuff in the Milky Way and start to get the nearby galaxies. Then you can use standard candles like the type 1a supernovae to get even farther than that. And then beyond that, you can do the Hubble Law, just measuring velocities of these receding galaxies and using the Hubble constant to calculate a distance to those galaxies. So these are all kind of independent distance measurements, and they don't all overlap. They work for different distances that you're measuring out in space. Okay, so let's talk about some of the other distance techniques that people have come up with. So this is the Wilson-Bapu effect. And so we've talked about when stars emit light, they emit light over all wavelength ranges. So that's what the definition of a black body is. We've talked about how some of those wavelengths will correspond to specific elements on the periodic table. And so what astronomers have done is they've mapped some of those chemical signatures to the absolute magnitudes of different stars. And so if you measure the brightness of a star at a very specific wavelength, then you know how bright the star should be, and you can calculate a distance using the apparent and absolute magnitude, or as the vocab words that we used before, brightness and luminosity. And this works for, again, up to the megaparsec range, so about 1,000,000 times farther than 1 parsec, which is the parallax angle of 1 arcsecond. Another technique we can use, so the Wilson-Bapu was for stars, Tully-Fisher is going to be for galaxies. So if we look at the, so when we look at the brightness of galaxies in different wavelength ranges, for example, if we're looking at the chemical signature of hydrogen for one of its emission lines, in theory it should be just one very narrow emission line. But when something is moving, and especially as galaxies move and rotate, those emission lines are no longer a very narrow peak, but they can spread out a little bit. So you can measure the width of those emission lines, and it turns out the width of those emission lines is correlated to the brightness of the spiral galaxies. So those emission lines widen as the galaxy spins at different rates, and so that's what this graph is showing. So this is the brightness on the x-axis, and you get the velocity of the rotation in the y-axis. And you can see it's not a super great graph, but there is some kind of linear trend in that graph. And so again, I can just measure the brightness of the galaxy by measuring the width of the emission lines. I can determine the absolute magnitude. So I have, again, a luminosity and a brightness. Luminosity and brightness mean I can measure a distance. We can also use gamma ray bursts to measure very far away distances in space. And so this will introduce a new concept called redshift. So for specifically using redshift to talk about distances in space. So the kind of the breakdown for this is that hydrogen absorbs wavelength for one of its absorption line features, Lyman alpha, at 121.6 nanometers. So any light that hits a neutral hydrogen at that wavelength range will be absorbed, and you won't detect that wavelength of light coming from your source. As light, and then for a gamma ray burst, the initial gamma ray is the high energy emission, but after that there's the afterglow that emits light at all wavelength ranges. Then as that light travels through space, because space is expanding, as a photon travels through an expanding space, it becomes redshifted. So the amount of stretching that the light undergoes is related to z, which is the redshift term. So z equals 0 is the current state of the universe, and so your observed wavelength and your emitted wavelength would be the same. But if I increase my z, I increase the amount of stretching that the light is going to undergo. Okay, so I have a very far away gamma ray burst. Any neutral hydrogen that's in between me and that gamma ray burst is going to absorb the Lyman alpha photons. This is going to create a dip in the spectrum that we call the Gunn-Peterson trough. And if you use some very specific filters on your telescope, you can look for these high redshift gamma ray bursts. So this graph is showing what one of these looks like. So for the gamma ray burst afterglow, you should see pretty much emission at all wavelength ranges. But there's this very sudden drop off around 7,500 or 750 nanometers, so somewhere in kind of the red filters. And so that doesn't correspond to any hydrogen absorption normally, but if the photon had been redshifted by a factor of almost 5, then that would correspond to the Lyman alpha absorption. So basically this gamma ray burst happened very far away, very early in the universe, and as the space between us and that gamma ray burst has expanded, that Lyman alpha 121 nanometers has been stretched all the way out to 750 nanometers. And so basically by finding where this dip is that would correspond to the Lyman alpha absorption, you can determine how far away these gamma ray bursts are. So this is another area of research that I do. We can also use gravitational waves to measure distances in space. So this is related to the change in frequency or the chirp of the gravitational wave signal. And you can basically do a bunch of complicated math to use that change in frequency to calculate a distance to this gravitational wave source. So this is a very new technique, and it works a lot better when you combine the gravitational wave source with an electromagnetic counterpart like a gamma ray burst or a supernova or a kilonova. Okay, so again, we've built up all of these different techniques to measure farther and farther out into space. And each one kind of acts independently. So we're not going to use the Hubble Law to measure distances in our galaxy. It wouldn't work. But we also couldn't use parallax to measure distances out to other galaxies because the amount of parallax is so small we couldn't measure it. Okay, so it turns out that the Hubble Law has more powerful implications than just measuring a velocity and getting a distance out. So let's say a galaxy is moving away from you at a rate of 0.1 light year per year, and it is 1.4 billion light years away. How long has that galaxy been traveling to get that distance away? Okay. So let's do the math. So we've got a velocity of 0.1 light year per year, and the distance is 1.4 billion light years away from us. So the definition for velocity is distance divided by time. So if we want the time, we need to do some cross multiplying. So move the t over and then divide the v over. So if we take this distance, 1.4 billion light years, and divide that by 0.1 light year per year, we get the light years to cancel, and now we have 1.4 divided by 0.1, and then billion years. So 1.4 divided by 0.1 would be 14, and so this was telling you that if you detect something moving at a rate of 0.1 light year per year, and it's 1.4 billion light years away, it would have taken 14 billion years to travel that distance. So, to summarize some of what we've talked about, we can use different techniques like parallax, standard candles, and the Hubble Law to measure distances to galaxies. And the Hubble Law is this velocity equals the Hubble constant times the distance. Or you can do velocity divided by Hubble constant equals the distance. But let's talk about the implication of everything moving away from us. So maybe for a minute, talk amongst yourselves. If distant galaxies are moving away from us, what happens if you rewind the clock backwards? Okay, I think I heard the right answer and people using their hands to show. So if you are expanding currently, then when you rewind, you have to compress back into some smaller shape sometime in the past. And so you can calculate the age of the universe by using the Hubble constant. So the age of the universe is just 1 divided by the Hubble constant. So by taking that basically census of galaxies and their velocities and their distances, you can use that to calculate the age of the universe. And when we do that, we get a value of about 14 billion years. So we think the universe is about 14 billion years old. And so what we're talking about is these galaxies themselves are not what are moving away from each other, but it's instead the space between them that is expanding. So if you think about drawing points on a balloon, as you blow the balloon up, those individual points are not moving along the surface of the balloon. It's just that the balloon is expanding, and so the space between the points is increasing, and that makes it look like those points or those galaxies are moving farther away from you. So this is why everything is moving away from everything else. It's not that the Earth is at the center of the universe and everything is expanding outwards. It's that you can think about everything being on the surface of a balloon and everything is moving away from you as the space between is expanding. And so this will bring us into some ideas that will set us up for talking about the evolution of the universe next class. So the cosmological principle is that there shouldn't be any special places in the universe. So there shouldn't be a center, there shouldn't be edges. Everything should be more or less evenly distributed. And we might come back to number 3. It has been consistent, but there's some new observations that are coming out that are maybe not all consistent with this idea. And so we've kind of talked about this before, but because light has a finite travel speed, the farther away you're looking in the universe, the farther back in time you're looking. So the first kind of grid, you have light being emitted from some supernova, and then that light is propagating through space, but as the light is propagating, the space between the two galaxies is expanding, and so it takes more time than you might have originally thought for that light to make it from one galaxy to the other. And this is also why the wavelength of that light is being redshifted, because it's being stretched as it travels along the expanding space-time. And so you can think about distance, but you can also think about it as a look-back time. So you're looking farther out in space, but you're also looking farther back in time. And so this is where that redshift that we were talking about comes from. So, for example, a yellow photon emitted during that supernova will be stretched, and so it'll be more red when it actually makes it to the observer in, say, the Milky Way galaxy. And so this idea of using the amount of redshift to talk about a distance is what is on this slide. So as the observer, we're going to observe some wavelength of light. That light might have been emitted at a different wavelength, and so using this equation, we can calculate how much the light has been stretched by. So z equals 0 is the current local universe. So your observed wavelength will be equal to your emitted wavelength. But if I set z equal to 1, then 1 plus 1 gives you 2. And so my observed wavelength would be twice as big as my emitted wavelength. So a z equals 1 means that the space has expanded basically by a factor of 2 in the time that light has been traveling. You can use the redshift z to calculate the speed divided by the speed of light, or if you've measured z and you know the speed of light is a constant, then you can use that to calculate a velocity. Velocity is one of the components of the Hubble constant, or the Hubble equation, and so doing the Hubble constant divided by the velocity gives you a distance, and so this is now another way to measure distances in space. So by measuring the redshift of some event, like a gamma ray burst, you can use the Hubble constant to calculate the distance to that gamma ray burst. So the fact that things are moving away from us, and the farther away you get, the faster they're moving, has implications that if you rewind the clock backwards, everything had to be at a much smaller and closer point at some time in the past. And by measuring the Hubble constant, you can actually calculate an age of the universe. So how far could you rewind backwards before everything is in one point in space? And that's about 14 billion years. So next class, we'll talk about the evolution of the universe, starting from what happens when you rewind everything back to everything being at the same point in space.